The industrially important separation of alkene-alkane mixtures is currently carried out in distillation columns. Let's consider, for example, the separation of ethene from ethane. The boiling points are relatively close to each other, and the relative volatility alpha is about 1.2. For separation of propene from propane, we see that the boiling point differences are about 5 degree Kelvin, and the relative volatility is only 1.14. Currently, industry requires ethene feedstocks to the polymerization reactor to be of 99.5% plus purity. And similarly, the propene fed to a polymerization reactor should also have a high purity of the unsaturated alkene. This is a picture of a distillation column. Typically, the distillation column for separation of propene from propane, this is called in industry as the C3 splitter. Such distillation columns are amongst the largest distillation towers on this planet. They operate at reflux ratios of about 15, contain about 100 plus distillation trays, and in view of the large capacity of such units, the column diameters can range up to 20 meters, and the column heights are about 75 meters. Just to put this in perspective, this is a picture of a human being, and you should consider the height of this human being in relation to the diameter of the distillation column. In view of the fact that these distillation columns operate at cryogenic temperatures, at high reflux ratios and high pressures, they are energy intensive because of the costs associated with vaporization and cooling in the reboiler and condenser operations. So in MOF developments, this separation has been the target for MOF, for the development of a suitable MOF as a replacement for the current distillation technology. Today, my presentation will focus on the separation of mixtures of ethene and ethane using cobalt gallate. The pores of cobalt gallate are such that the ethane is virtually excluded due to diffusional limitations, and the adsorption and diffusion both favor the alkene. And in a paper just online in Separation and Purification Technology, researchers from the Zhejiang University in China have reported the use of cobalt gallate pellets in a vacuum swing adsorption process. And I'm going to discuss some details of their findings. Watch also my previous presentation on alkane-alkene separations with MOFs, metrics for the evaluations of MOFs and transient breakthrough simulations on my YouTube channel. But let's focus on cobalt gallate pellets in PSA operations. As discussed in my paper published in 2020, a PSA scheme for separating ethene from ethane would consist of the following steps. We have pressurization. We have the adsorption cycle, in which the feed mixture is fed to a fixed bed, and purified ethane is recovered from the top of the fixed bed. This is followed by a co-current purge or co-current rinse step, in which a portion of the product ethene is used to purge the contents of the adsorb phase, such that any residual ethane is desorbed, and that can be mixed along with the feed mixture and fed to the adsorption cycle. The co-current purge or co-current rinse stage is followed by co-current blowdown, in which vacuum is used to remove the remainder of the adsorbed phase components within the fixed bed, and the products that are withdrawn are mixed along with the feed mixture and fed to the adsorption phase. The last step is a countercurrent vacuum blowdown, in which the desired product ethene, hopefully of the required purity for making polymer grade polyethylene, can be withdrawn from the bottom. The need for all these intermediate steps, such as co-current rinse and co-current blowdown, is that any ethane that is present in the void volume or in the adsorbed phase will contribute to low purity of ethene in the product, and therefore we need these two intermediate steps before the countercurrent vacuum blowdown. Rather than use the 5-step PSA scheme shown in the previous slide, the authors of this paper, published in Separation and Purification Technology, use a slightly simplified PSA scheme consisting of pressurization, the adsorption cycle, co-current rinse, and countercurrent vacuum blowdown. In other words, the co-current blowdown step is avoided in the simplified process scheme. Furthermore, the simulations for separation of 80-20 mixtures of ethene and ethane at a pressure of 1 bar and temperature 298 Kelvin are carried out using the Aspen software that is limited in its applicability because it can only handle the LDF approximation. For further details of the LDF approximation, I refer you to my presentation on this topic on my YouTube channel. The important point I would like to make is that the results of the use of this simplified PSA scheme with the simplified LDF approximation are summarized in a table in their paper, in which the purity and productivity per cycle of purified ethene are presented. I invite you to look at the productivity per cycle, and depending on the choice of the operating conditions, the maximum productivity that is achievable in the simplified PSA scheme is 1.6 moles per kilogram per cycle. Just to highlight this aspect of productivity, I present here IAST calculations for 80-20 ethene mixtures at 298 Kelvin and 1 bar in cobalt gallate pellets using the isotherm models that are provided in this paper. The adsorption selectivity is 54, and the maximum productivity of purified ethene can be calculated from the IAST based on the shockwave model. And the shockwave model is discussed in my previous presentations on my YouTube channel, also in my published papers. And the separation potential, which is derivable from the shockwave model, leads to the determination of the maximum productivity that is achievable in PSA separation, and this is 2.8 moles per kilogram. So one wonders why in this PSA scheme that is described in this paper, the maximum achievable productivity is only 1.6 moles per kilogram. And I'll proceed further to dissect and analyze the separation to understand why the productivity that is reported in this paper happens to be significantly lower than the value of 2.8, that is the maximum achievable. For separations in fixed bed adsorbers, in which intracrystalline diffusional influences are of significant importance, as is the case for ethene-ethane separations with cobalt gallate, it is vitally important to adopt the Maxwell-Stefan diffusion formulations to describe the intracrystalline molar fluxes. In the Maxwell-Stefan formulation, the intracrystalline flux for component I is related to the chemical potential gradient of that component. The chemical potential gradients can be related to the gradients of the molar loadings Q via a matrix of thermodynamic correction factors gamma sub ij. All of this is discussed in my previous papers that are listed here. See also my video presentation, The Need for the MS Formulation in PSA Modeling. A simplified form of the intracrystalline diffusional flux is to adopt the Fickian formulation, as is done in the LDF approximation, where the thermodynamic correction factors are ignored, and we say that, or we assert that the fluxes are proportional to the gradients in the molar loadings via the intracrystalline diffusion coefficients D sub I. For 80-20 mixtures, the simulations for the adsorption cycle using the Maxwell-Stefan formulation are shown in the continuous black line here and the dashed black line, whereas the simulations using the simplified LDF approximation is shown by the blue line. The x-axis is a modified time parameter in which Q0 is the inlet flow rate in liters per second multiplied by time in seconds divided by the kilogram of MOF, in this case cobalt gallate, that is packed inside the fixed bed, and this has the units of liters per kilogram. We see that the separations are significantly better by adoption of the Maxwell-Stefan diffusion formulation. This is indeed the common theme that is observed for several different microcrystalline porous hosts, as is discussed in my published work. Let's examine what would happen if I carried out the PSA simulations for 80-20 ethene-ethane mixtures using the Maxwell-Stefan formulation instead of the LDF approximation. Using the 5-step PSA scheme for 80-20 ethene-ethane mixture separations using cobalt gallate, I carried out simulations for a PSA scheme. The concentrations leaving the fixed bed adsorber in the adsorption cycle are shown here, where this is ethene, the blue one is ethane. So the adsorption cycle would be terminated at say a time of 1000 seconds. The component loadings for ethene and ethane along the height of the fixed bed adsorber are shown here with the units of moles per kilogram, and this is the these are the adsorb phase loadings at the end of the adsorption cycle that is terminated at 1000 seconds. The adsorption cycle is followed by a co-current purge or co-current rinse, in which the components in the adsorbed phase are purged out or rinsed out, and in particular we note that the ethane is rinsed out of the column, and the compositions at the end of the co-current purge, which lasts for 50 seconds, the component loadings along the height of the adsorber are shown here, black for ethene and blue for ethane. The co-current purge is followed by co-current vacuum blowdown, in which any remainder of the ethene is purged out of the column, and the purged gas ethene and any residual ethane is mixed along with the feed mixture and fed to the adsorption cycle. The component loadings at the end of the co-current blowdown phase that lasts also for 50 seconds are shown here. Black lines are for ethene and the blue lines are for ethane. The final step is the countercurrent vacuum blowdown, in which high vacuum is applied and the contents of the fixed bed adsorber are purged, and the cumulative amounts of ethene and ethane expressed in moles per kilogram are plotted here as a function of time. the productivity of purified ethene per cycle is 2.2 moles per kilogram compared with the maximum of 1.6 moles per kilogram that was achieved by the authors from Zhejiang University using the LDF approximation. So use of the Maxwell-Stefan approximation along with a 5-step PSA scheme is vitally important in the PSA process calculation, because it predicts that we may recover 2.2 moles per kilogram per cycle. So the use of the LDF approximation will lead to overly pessimistic productivities for purified ethene. So the takeaway message for my presentation is that use the LDF approximation at your own peril. For PSA modeling, it is important to properly account for thermodynamic coupling effects and adopt the Maxwell-Stefan formulation. And a complete 5-step PSA scheme is required for ethene-ethane separation, in which intracrystalline diffusional influences are of significant importance. To further drive home the message of this presentation, I carried out simulations for separations of 80-20 ethane-ethene mixture using cobalt gallate with a simplified 2-step PSA scheme consisting of the adsorption phase with countercurrent blowdown. The cumulative moles of products recovered after countercurrent blowdown for ethene and ethane are plotted here as a function of desorption time, and the productivity of purified ethene is 2.04. So using a simplified 2-step PSA scheme leads to a slightly lower productivity of 2.04 in place of 2.2 moles per kilogram for a 5-step scheme. But even this value is higher than the value obtained by the authors from Zhejiang University. The important point, of course, is that in these simulations, I adopt the Maxwell-Stefan diffusion and formulations, taking due account of thermodynamic coupling effects. Watch also my video on the need for use of MS formulation in PSA modeling on my YouTube channel.